Next, let's talk about the kinetics of substitution reactions. This information was greatly developed by Henry Tauby in 1952. He actually came up with two terms to define the kinetics of substitution reactions. Labile, which means that the coordination compounds react readily. The ligands pop off very easily. They're not bonded very strongly. They have these reactions for labile complexes have half-lives on the order of 1 minute or less, as defined by Tauby. Inert complexes are compounds that react very slowly. For some reason, the bonding between the metal cation and the ligand is very strong. These compounds have half-lives greater than 1 minute. Now, I don't want you to confuse kinetics and thermodynamics. You should never confuse the reactivity of a coordination compound with its stability. Reactivity is a kinetic term. Stability is a thermodynamic term. So labile and inert are kinetic terms. They define the speed of the reaction, not the stability of the reactants or the products. Stable and unstable are thermodynamic terms. So for example, FeH2O5F2+ has an equilibrium constant much greater than 1. So that means this compound wants to be formed. But it's also very labile, meaning that the H2O ligands or the F ligand will pop off very easily. A little more on thermodynamics versus kinetics. Let's look at the following reaction that we've looked at a little bit, we looked at a similar one earlier. CONH363+ reacts with acid 6H3O+ to give COH206-3+ plus 6NH4+. Now, it says that thermodynamically, you can look it up, delta G naught, that is the Gibbs free energy. If you're not familiar with that, learn more about Gibbs free energy. The Gibbs free energy is less than 0, that means it's negative, and the equilibrium constant for this reaction is about 10 to the 30th power. That means this reaction will occur spontaneously. CONH363+ is unstable in the presence of H+ and wants to form COH206-3+. Now, the activation energy for this reaction is very large. Even though this compound is unstable in acid, the reaction is slow because the compound is inert due to its large activation energy. This reaction, even though it will happen spontaneously, takes a very long time, on the order of days, to come to completion. So how do you determine if a compound is inert or labile? Well, you look at the electron count of the counts of the transition metal. This is a set of general guidelines. This is not absolute. Transition metal cations that will form inert compounds generally have D3 electron configurations, low spin D4, D5, and D6 electron configurations, strong field, which is low spin, D8 electron configurations in the square planar conformation, 4D and 5D cations. So anything below the first row generally forms inert compounds, or the first row of transition metals forms inert compounds. Compounds that contain metal cations with a weak field D8 electron count are going to be called intermediate. They could either be inert or labile. Finally, The compounds that are labile have very low d electron counts or very high ones generally. D1, D2, high spin D4 through D6, D7, D9, and D10. Now, first row transition metals are generally labile, almost all of them, except CO3 and Cr3+. Most second and third row transition metals are also inert. I want you to think about this, and this is discussed in your textbook. Why is this statement true? So we've talked about substitution reactions. Let's move on to dissociation reactions. Reactions involving a decrease in coordination number. So let's look at an example. You start off with COH206Cl2, and it's a red color, and the coordination number to cobalt is 6. You add heat, and you end up forming COCOCl4 solid. This is a blue compound and has a coordination number of 4. By removing all the water, you change the coordination number to cobalt in the complex anion. Addition reactions. Once again, another set of reactions that are fairly easy to tell what's going on. Dissociation is the removal of a ligand. Addition reactions involve an increase in coordination number. Most addition reactions occur in complex with low coordination numbers. So, for example, AlOH3 solid has a coordination number of 3. If you add some sodium hydroxide, OH-, you end up getting AlOH4 1- and increase the coordination number by 4. Dissociation reactions decrease the coordination number. Addition reactions increase the coordination number. Next, to oxidation-reduction reactions. Oxidation-reduction reactions, as you know from general chemistry, involve a change in the oxidation state of the metal cation. There must be an electron transfer during this reaction. Here's an example. Ruthenium bonded to 6 amine groups. They're neutral ligands, so ruthenium has a 3+ charge. It can react with Cr2+. An electron is transferred from the Cr2+ to the Ru3+. So now the complex is RuNH3 6 2+ plus Cr3+. Note, there is no change in the coordination number or the ligands bonded to the transition metal cation in the oxidation-reduction reaction looked at here.